Welcome to Chapter 3, Systems of Linear Equations. And we're going to begin in Section 3.1, using graphs and tables to solve systems. So what a system is two linear equations and two variables. And now we're going to be finding solutions to actually both equations. And we're going to be solving systems with tables, equations, and graphs. So here's an example of a linear equation in two variables. So notice we have two equations, and now if we want an ordered pair solution, it has to work in both the top and the bottom equation. So just like a single linear equation in two variables, we are interested in finding solutions. To the system. And in this case, a solution of a system is an ordered pair XY that satisfies all equations in the system. So it has to work in the top one and the bottom one. All right, so let's do a little bit of exploring. We're going to take those two equations, 2x plus 2 and negative 3x plus 7, and we're going to make kind of a three-way table. Whoops. Okay, so it's an xy table. Let me just show you how this works. This x negative 2, we're going to plug it in here, right? So, and get our solution. We're also going to take negative 2 and plug it in here. So we're going to get two ordered pairs. So let's see how this works. So this is going to be y equals 2 times negative 2 plus 2. So negative 4 plus 2. And then we're going to plug in negative 2 to in our second equation. So positive 6 plus 7 is 13. Okay, so let's take a moment to finish in our table. I'm going to do this trick. We did this before when we were talking about slope. Notice we're increasing by 1. So since our x values are increasing by 1, our y values are going to be increasing by the slope. So a fast way to do this is just to add the slope 2 to all the y values. So I'm going to do that trick. So negative 2 plus 2, 0 plus 2, 2 plus 2, 4 plus 2. Okay, so I just added the slope to get the numbers in blue. And you can definitely, start from scratch. For instance, with y equals 1, or x equals 1, we could have done the y equals 2 times 1 plus 2. And that also would have gotten us 4. Okay, so just different strategies. All right, but sometimes it's nice to work smart. Same thing over here. Let's decrease now by the slope negative 3. So 13 minus 3, 10 minus 3, 7 minus 3, and 4 minus 3. Okay, so again, how this is working is this is giving us ordered pairs. So this is like negative 1, 0. And over here, x is negative 1, y is 10. All right, so we're using one x column for two y columns. All right, so why are we doing this? We're trying to solve the system. So a solution would be an ordered pair that satisfies our first equation and our second equation. So do any of these have the same ordered pair? The same x value maps the same y value. All right, and then it's this one right here. When x equals 1, y equals 4 in both of these solutions. So let's write that out. Since 1, 4 works with both equations. We say that it's a solution. One, 4 is a solution to the system. All right, so that's how we would solve it. We would say 1, 4 is a solution to the system. Okay, so some questions to ask ourselves now. Are there more solutions? So we found 1, but are there more? The other thing was we got kind of lucky because we started our x values right around 1, right? And it also happened to be an integer. So what happens if the solution happened at x equals 1/2? Or even what happens if the solution was at x equals 20, right? And we're looking at values at -2. So this isn't the most efficient way to get solutions. It happened to work in this case, creating a table and finding the common y values, but it's not a good solution. Or it's not a good way to find the solutions. So we're going to develop more techniques in section 3.2, but let's look at this aspect visually. So ordered pair being the solutions to both equations. So we're going to look at this visually. Let's examine the graphs of each equation of the above example, since a graph represents all ordered pair solutions. Okay, so I have this little xy plane. Let's have this be the y-axis. Have that be the x-axis. Our scale can be just 1, 2, 3, 4, 5. Just one tick is 1. 1, 2, 3, 4, 5, 6, 7, 8. All right, so let's graph it. So this is in y equals mx plus b form. So we have a slope and a y-intercept. I'll graph the top one in red. So remember, in this format, we start with the y-intercept 2. And then we use our slope to find the next point. So 2, let's think of that as 2 over 1. So we're going to rise 2 and run 1. Up 2 over 1, new point. Up 2 over 1, new point, etc., etc. All right, so this line in red represents all ordered pair solutions, hopefully yours is straighter, to y equals 2x plus 2. Let's do the same thing for our second line. I'll do it in blue. So we start at the y-intercept, which is 7. 1, 2, 3, 4, 5, 6, 7. And now our m is -3. So we can think of that as going down 3 and over 1. So 1, 2, 3, 1. 1, 2, 3, 1, etc., etc. And now if we connect the dots, that blue line represents all ordered pair solutions to y equals -3x plus 7. Okay, so notice then, if the lines are all the ordered pair solutions, there's only one point in common to both the lines. So that means there's only one ordered pair that works for both the blue line and the red line, and that's that point of intersection. And notice, too, that that happens to be exactly what we found in our table. It's the ordered pair 1, 4. And that's our solution. That's our solution. So the intersection point is our solution. And then we can ask ourselves, are these lines going to intersect again? No. So now we know it's our only solution, because lines aren't going to intersect more than once. Okay, so that answered our question, if we remember, are there more solutions? In this case, no. The lines only intersect once. There's only one ordered pair in common. So in general, the points of intersection are the solutions to the system. And with lines, they only intersect once in this case. Okay. And again, this is limited to because what if our solution didn't happen at x equals 1? What if the solution happened at x equals 0.6? And so now we're relying on an estimation rather than the exact answer. So the table method of finding solutions has limitations, and graphing solutions of systems also has limitations. Okay, so we are going to generalize the types of solutions we have for linear systems. Okay, and we're going to look at 3 different cases. So we'll just draw 3 different generic xy planes. And think about linear graphs. So in this example we just had, our graphs crossed. And there was one solution. How else can lines interact? Well, do all lines intersect? No. Parallel lines never intersect. So that would mean 0 solutions. Any other possibilities? Well, what if we have one line like this, and then the other line was right on top of that line? In other words, it's the same line. In this case, they intersect infinitely many times, right? So we have those different types of solutions for linear systems, all right? So again, the point of intersection are the solutions. If they intersect once, it's one solution. If they're parallel lines, it's 0 solutions. And same line is infinitely many solutions. And then we have some vocabulary words to go along with this. If they have solutions, they're consistent. So if they have solutions, they're consistent. So one solution is a consistent system. Infinitely many is a consistent system. And then if there's no solutions, that's inconsistent. All right, so I'm just going to box that. So it's inconsistent if there's no solutions. And then, furthermore, if there's 2 separate lines, those lines are independent. So intersecting lines and parallel lines are 2 separate lines, so those are independent. But if it's the same line, it's a dependent system. And there's infinitely many solutions. So I'm going to put a box around that one. Okay? So there you go. All right, so now's the time to kind of explore this a little bit. So feel free to push pause and then come back and check your solutions. Okay, so let's see how we're going to approach this. So is this system a dependent system, an inconsistent system, or a one solution system? Okay, so again, going back up, dependent system means the same line, inconsistent is parallel lines, one solution system is it intersects once, 2 separate lines. All right, and then notice here, we have the same slope and different y-intercepts. Okay, so same slope tells us we're in one of these cases, inconsistent or dependent. Parallel lines have the same slope, same line has the same slope. Because the y-intercepts are different, it's a parallel, there are 2 parallel lines. If the y-intercepts were the same, it would be the same line. So we have the same slope, different y-intercept, that tells us parallel lines. So same slope, different y-intercept. That tells us that these are an inconsistent, or this is an inconsistent system. All right, and now let's look at this system. So y equals 3x minus 5, y equals mx plus b. Find values of m and b such that this system is inconsistent. Well, if it's inconsistent, it has to be two parallel lines. Parallel lines have the same slope, so n has to be 3. And then our y-intercept has to be different. So you can choose b just that's not negative 5. So for instance, I could choose 0, 1, 2, 3, 4, 5, something like that. So this is going to be an inconsistent system. And what's the solution set of the system? There's no solution. So how we write that is we can write no solution. A solution makes up a set, so we could say it's an empty set, something like that. All right, because parallel lines never intersect. Points of intersection are solutions. No intersection points, no solutions. All right, and now we want to find values of m and b where the system is dependent. All right, so if it's dependent, it means it's the same line. So our slope has to be 3, and our y-intercept has to be negative 5. So now it's the same line. And what's the solution set of the system? We could say infinitely many. We can also say that when y is equal to x, when x is x, y has to be 3x minus 5, right? That's the original equation up here. Y equals 3x minus 5. Okay, and now find values of m and b such that the given system is a one-solution system. Well, in that case, all we want to know, let's go back up to our visuals. We just want to make sure that the lines are not parallel. We want to make sure the line isn't the same. So we can do this by just making sure the slopes are different. If the slopes are different, they're going to intersect. So let's go down, and you can write something like m just is not 3. So you can be as creative as you want. You can write like negative 3/4. You could write just 1. Something like that. Just make sure it's not 3. And then b, again, infinitely many things to choose for b. You could actually even choose the same y-intercept. That's not a big deal at all. You can choose the y-intercept to be negative 5. You could choose the y-intercept to be 2. All right, the most important part is that your m is not 3, and then you're good to go.